Hi everyone, and welcome to the lecture guide for Module 6. So this is going to be quite a big module. It's going to take us 2+ weeks to go over. So it'll be the module that we're focusing on for this week and the next week. So that's shown in the little calendar I gave on Blackboard, and you can hear me talk about that in the video that's attached to that calendar. So why is this so big? What's going on in this module? Well, first things first, there's tons of vocabulary, as you can see here. Some of it, though, will be review, things we've talked about already, but some will be new stuff. So, for example, we've talked about the mean. I want you to be reviewing lots of this notation, but we're going to introduce the median, the idea of an outlier, standard deviations of specific things, so not just standard deviation, but the standard deviation of a sample and a population. We'll talk a little bit more about these distributions and the shapes that they can take. We're pretty used to a normal distribution, but we'll talk about two other variations of that. And then finally, we're going to put a term on something we've already seen, and that's the standard error. So you can see here the topics of this module broken up by section. And you see the first three are all actually going back to section P.2. And so what we're going to do is we're going to take a little bit deeper dive into the idea of the median, the mean, and the standard deviation. And you're going to be looking at problems where you have to take some data and try to get a feel for each of these quantities. And one big thing we're going to want to talk about is this third dot here. So let me highlight it. Understanding the effect of outliers on the mean and median. So the basic idea here is we're going to be talking about if we have a data set where there's a few pieces of data, maybe only one, but maybe a few, that really don't fit the pattern of the data. They're really large compared to everything else, or really small. That's the idea of an outlier. And we've been using the mean to talk about the middle of our data up to this point. But in some situations, it's really not the best way to talk about things. So the mean, as an example, can change pretty drastically if you put one large outlier into your data set or one really small outlier. And that's bad because we don't want one piece of data or only a few pieces of data to have such a massive effect on how we summarize our statistic, our data. And so we'll see that the median does a much better job at not getting pulled one way or another because of an outlier, right? But there are some issues with using the median in terms of trying to actually do the math that we've done. So we'll look at that, and we'll have to just kind of talk about the balance between those two things. What makes the math easy versus what does a really good job actually describing what we want to look at. So describing our data. Then from there, we're going to jump into sections 1.5 and 2.2, which are all about the theoretical approach to hypothesis testing. So what we're going to do here is we're going to do the same process over again. Set up my null and alternative. Here's my statistic. Give me a null distribution. Find my statistic on there. Get the p-value or the standardized statistic and use that to tell me, was I too extreme? Do I fit the picture? What's your conclusion? That process, we're going to do it again. Here's the difference though. Instead of simulating the null distribution, having a computer do it by us telling it some information, we're going to use formulas to create it instead. I know that's a little bit weird. What do you mean we're going to use a formula? We have the ability, under certain circumstances, to just completely predict what the null distribution should look like. It's crazy sounding, but I'll show you that instead of having to have a computer simulate sample, we can predict what that process would result in just from knowing a few pieces of information. And then we can use that model that we've created by ourselves, by hand, in order to test our statistic. Unusual, usual, plausible for the null, or throw out the null. I think it's the alternative. So it's the same process we're going to do, but we're going to find a different way to do it. And it's kind of a historical way to do it. Okay, so let's look at some of the terms then. So we know the population mean and the sample mean. We've done this before. Mu x bar. Nothing new. The first new thing is the outliers. And so you're going to read this definition and maybe not feel great. It just says data that is markedly higher or lower than most of the data. And so it's kind of like, well, what does that mean, right? Well, what we want to do here is we want to get a picture of our data, look at it, and then think about any data points that don't fit the pattern, similar to how we did the unusual, usual samples. There are ways to try to measure if something is an outlier, but depending on the resource you're using, the way that they do it might be different. And so at this point, we're just going to say, just look at it. Is the data point, each data point, I look at your data point, is this extreme or does this kind of fit with everything else? And that's how we'll call something an outlier. So we'll practice that. Okay, so we've got two measures of centers here. Again, mean, you've seen, it's just the average, what's, about the middle, right? Add up all the values, divide by the total number, okay? And then now we've got the median. This is we measure the center of our data set, right? But here's how we do it. We line up all of our pieces of data in a row, and we do it in order, smallest to biggest, okay? We line them all up. We just cut our list, take a knife and chop it right in the middle. That's the median. If we end up hitting a number, there is a data value that is perfectly in the middle, that's our median. If we end up between two of our data values, we average them, that's the median. So we're basically just trying to take the entire data set and perfectly cut it in half. The mean does not work that way. The mean is not going to necessarily cut your data in half. And we'll see some examples of that. But the idea is if you've got any outliers, any data points really big or really small, then your mean will be pulled towards those numbers, right? And that will mean that it won't actually cut your data in half. But we want center, right? Measure of center. So it should make sense that we want that number we find to be halfway in between. So sometimes the median can be better than the mean in actually describing to you what's in the middle. So we've seen standard deviation already, how far away the data values are from the mean, what's the spread. What we haven't seen is the notation here. So we have seen little s, that's the sample standard deviation. But if you have quantitative data, right, then your population also has a standard deviation. Because quantitative data, you've got numbers. What can we do with numbers? We can average them, which means we find the mean. And as soon as we do that, we can find out how spread the data is. So again, we've got two symbols here. One for the sample standard deviation, little s, all right? One for the entire population's standard deviation, okay? This is little sigma, another Greek letter. So we're going to add that to our little list of Greek letters and not Greek letters. Population, sample. And finally, the standard error. What's the standard error? Well, we're just putting a name on something we've already seen before. This is the standard deviation of your null distribution or your chance model. All right, so remember what we've done in the past. We made a simulation that pretended to be you or the experiment that you were running, and we did it a bunch of times, assuming the null hypothesis. Gave you that nice picture, and then we could click a button that said what was the standard deviation of that picture, how spread out were your samples in your sampling distribution. Well, we looked at that. Sometimes we saw it was pretty spread out, sometimes it was pretty packed in, had the general bell shape to it. But we also used that, right, when we did the standardized statistic, right? So the standardized statistic, we've used this number. That was always the bottom number in our formula. So remember the formula is stat minus mean of the null divided by standard deviation of the null. So we're just, instead of on the bottom now writing standard deviation of the null distribution, blah, too much, we're going to call it the standard error. Make it easy on ourselves. Okay, so we're just giving a name to this thing. We've already seen this, just putting a name on it. So you just got to get the name in your head. Okay, and so the last piece of this new stuff is looking at the shapes of distributions. So we've seen this bell-shaped distribution many, many times before. Sometimes you'll hear it called normal, right? Most things are in the middle. You got about equal above and below the mean, and you get these little tails where your extreme values are. But not every distribution has to look like that. If you have outliers, right, you can have distributions that are right skewed, left skewed. You don't necessarily need outliers for this, but sometimes you're going to have data where most of your data is packed together in one place, but you do have a good amount of data points that kind of stretch out to the right. That's called right skewed. So you've got some data points here that if you look at these, they are pretty big compared to this big group here, right? Most of the data points are here, but you've got some that are pretty far away. What's that doing? Well, I know it's a little tough to see. Let's zoom in here, right? What that does is it takes the mean and brings it to the right, because these big data points count for a lot. What is the mean? You add up all the values. So if I'm adding up all the values and I get really big numbers to throw in, those are going to have a big impact on my addition. So then a couple big values are going to take the mean and pull it over to the right. But the median doesn't care about that. All it cares about is saying what is 50% right in the middle of all my data. And so this median does a better job for us describing where the middle is, where this mean doesn't quite do as good of a job because it's getting pulled towards the big numbers, right? The median doesn't care if you're extreme or not extreme, right? Every point is being counted the same amount. The mean, that's not true. Big points or very tiny points will have more of an impact than just kind of a normal point. So this can work the other way too. You could be left skewed, so you notice the tail goes to the left. And this way your mean gets dragged lower than your median. If you have lots of smaller values here, they will count for more when you're trying to do the mean. Right? I guess they count for less, but we'll say it the other way. They're more important in the mean calculation. And so even though maybe the middle, really you'd want the middle here, because that really describes 50% on either side, the mean gets pulled off in the direction of the outliers or the more extreme values. So the mean here is not doing quite as good of a job describing things to us. Okay, so that's bell-shaped, right skewed, left skewed. So moving on, we are now at the point of looking at the theory-based approach to the processes we've done earlier. So what I'm going to do here is I'm going to show you what our overall process looked like before this module, and then I'm going to show you what it's going to look like after, and there's just one little change. It's going to be really nice because it'll give you practice on the Unit 1 stuff, and if you were already at the point where you were kind of clicking, feeling good about the Unit 1 stuff, you're going to realize, oh, look at this. Unit 2, I'm just doing the same thing. All I have to do is change one way I'm calculating something, and it's the same thing. So you'll feel really good. So let's think about this. So up to this point, we're going to start right here. Up to this point, to run a hypothesis test, we did the following. We created a null and alternative hypotheses, right? So our null hypothesis at this point looked like pi equals, if you're categorical, or if you're quantitative, it looked like mu equals. So these were the two different null hypotheses that we had made. Once we did that, right, we then went to the computer and said, hey computer, here's my null hypothesis, assume this, here's my sample size, give me 100 or 1,000 simulated samples, and I'm going to look at the picture you give me, right? So this is in blue. This is what we've done so far. Go to the applet, make your picture. Then what did we do? Well, early in the class, we took our statistic, like Buzz and Doris's 15 out of 16 or whatever we were looking at, and we looked at the picture and said, does my statistic fit? Is it usual? Or no, it's unusual. It's far away from the middle. It doesn't seem to fit. We made a conclusion based on that, and what we've done recently, so right at the end of Unit 1, was we said, I don't want to guess anymore. Let's get the p-value or the standardized statistic, right? If I get those two numbers, I can tell you for sure if we are unusual or usual, right? So I have a numerical way and cutoffs to say, I'm going to calculate this number. Okay, I get this number, you're unusual. I get this number, you're usual. What do we do with that information? We either conclude the null is plausible or we have support for the alternative. So that's the process we've been doing over and over again. So what changes in the theory-based approach? Well, let's go look. Step 1, create a null hypothesis. Still looks like pi equals, still looks like mu equals. Categorical, quantitative. No change. Here is where the change happens. Instead of telling the computer, hey computer, we're going to simulate a bunch of samples and then I'll go look at what they look like, right? No, we don't do that. Instead what we do is we create a theoretical sample distribution. So instead of saying computer, go simulate a bunch of these and I'll kind of get the rough picture, I know what the sample distribution that the computer's doing, your chance model, should look like before you even do any of it. I know it's crazy sounding, but we're going to see that it works a lot of the time. We have to be a little careful, but we'll see that it works. And just historically, this is what was done before computers. And it's still done today. You can still use this method most of the time, and you're fine. But this is what they did before computers because they didn't have computers that could do all these simulations for them. So we still then move to the next step. We've got our picture in blue here. We get our picture. We figure out usual, unusual. Again, your p-value, your standardized statistic. And then we make a conclusion. So that's it. One difference. Zoom out a little bit more. Blue to blue. And it's just, how do I make my picture? That's the basic idea, is how do I make that picture? Either a computer simulates it, or I use the theory to create it myself with a couple calculations. Done. Pretty nice. We also will have the computer do the calculations for us in general. So, you know, it's there. Why not? Okay, so then what do I mean by this idea of a theoretical sample distribution? So let's look at a couple examples that we've already played around with. So in previous sections, we've seen pictures like this, okay? We've got the Yummies purchases here. Remember we had that picture. So for this example, let's just pretend that the null hypothesis that we assumed was 0.4. So look what happens. When the computer goes simulates, you get 0.4 in the middle because we told it that, right? We said computer, 40%. Boom, put me right there. Okay. We get some higher, some lower, but most of the samples are right about in the middle with some extreme on both sides. Okay, next example. We've got some other proportion here. We told the computer, I think the proportion's 0.8. Okay, computer, simulate me some samples. What happened? 0.8's in the middle, you get some higher, some lower, and you got a nice little bell curve. Bell curve. Okay, so maybe you're thinking, we just got lucky, or maybe that's only true for proportions. Well, what about means? We go to means, we tell the computer, hey computer, our population average is 315, go simulate some samples for me. It does it, 315's in the middle, you've got some lower, some higher, and you've got roughly a bell shape here. So every single time the computer did the simulation, we got a bell curve, a bell curve, a bell curve. We got the middle is predictable. It's exactly where the computer thought it should be. It's what we told the computer. Hey, put the middle here. When we say null pi equals 0.4, pi equals 0.8, mu equals 315, we're telling the computer middle here, middle here, middle here. So, number one, we think it should be a bell curve. Check. Keep that in your head. Number two, we know where the middle will be just by knowing the null hypothesis. Hold on to that. The only piece of information we don't know is how spread out should this picture be. I've got the first two things, and I could draw the picture, but it's not going to quite work unless I also know how spread out things should be. And so that's all we're missing. But in general, again, we know where the center should be. We know what the shape should be. And this culminates in a theorem. This is our first real theorem in this class. It's called the central limit theorem. Here's what it says. If you draw random samples of size n, think about that. That's what we told the computer to do, right? Give me samples of some sample size. 10, 20, 35, whatever it is, but I'm going to call it n here. The distribution of the sample statistics, aka our picture, approaches a normal distribution. Normal was that perfect picture, right? So see how this isn't perfectly normal, right? It's not this perfect curve. But the central limit theorem says, well, if you keep increasing the sample size, n, you keep taking a bigger sample, then this picture will get closer and closer and closer to being this perfect curve. So what this tells us is that if we pick a single sample size, then we will be able to approximately get a normal curve here. The bigger the sample size, the better the picture, which is nice, but it's not necessary, right? If we're approximately normal, then we can still do things like the p-value, the standardized statistic, all that stuff. So what this is saying is we increase n, we can make it perfect, but perfectly normal, this perfect nice picture. But if we can't, we just only have one sample size, this is saying we could still do a pretty good job approximating the normal distribution. So what does this mean? It means that simulating has been us trying to get to this perfect bell curve that exists theoretically. We've been trying to get at that this entire time. We're just approximating it. We're saying, okay, we can't quite get this perfect picture yet. We don't know the formulas. We don't know the theory. But by simulating, we could get pretty close. And these are pretty good. These are pretty close. They're not perfect, but they're pretty close. So, how do we then apply this in our scenarios? So scenario one is we've got one proportion, right? So how do we apply the theory-based approach for a proportion? Remember, categorical. Well, number one, we've talked about this. We know the middle of our picture. It's whatever the null hypothesis value for pi was. If you told me pi was 0.5, I just can write that down. That's the middle of my picture. If you tell me pi is 0.33, I just go draw the middle of my picture right at 0.33. Just done immediately. The next piece, which we're not going to actually really talk about, we're just going to have to keep this in our head, although you'll have formula sheets, so you don't need it in your head, is that the standard deviation, the spread of our picture, is given by this number, or this formula, the square root of pi times 1 minus pi over n, where pi is just, again, that's our hypothesized value. What's your null hypothesis say about pi? That's what goes in here, right? And n is your sample size. So let's stop here and think about this. Think about what I'm saying. I'm telling you that I can predict each of these pictures, again, not perfectly, but close. I can predict all of these pictures and then go find you a p-value, a standardized statistic, make a conclusion. All of that can be done from what? From knowing the hypothesized pi value, so null hypothesis, number one. Number two, your sample size. If you give me those two pieces of information, I can do all of that work. That should be crazy sounding, but it does work. Again, there are conditions where we need this to be true. But in general, in most situations you're going to see, all you need to tell me is your null hypothesis and your sample size, and I will give you that picture. Pretty crazy. So then what can we do with it? We can still find a p-value. We can still find a z-score. We have the picture, right? That's all you need. You need the picture, and you can do those calculations. You can kind of quote-unquote count your dots, right? There's no dots anymore because it's that nice, smooth picture. But we can have the computer kind of quote-unquote count the dots for us still. We can still take a slice of that and go, okay, how much is to the right if we want to do greater? How much is to the left if we're doing less than, the more extreme? And we can definitely do the z-score because we know our stat, we know the middle, and we know the standard deviation, or the standard error in this case, because that's the formula. So quick, really nice. Now, we just have to be a little careful. To use this approach, this is important, to use this approach, the theory-based approach, we need to make sure that in our data, we've got 10 successes and 10 failures each, right? So what does that mean? Well, we set up all of our categorical variables to be two options, right? Binary. We were doing that earlier too, right? Either it was a Yummies purchase or not a Yummies purchase. Either it was a scissors or not a scissors, right? There were actually three options there, but remember we stuffed two of them into one option. So we could do scissors, not scissors. Right, so any categorical variable, remember we put it into two options, and then as long as we've got 10 successes, whatever we want to say is success, Yummies purchase, throwing scissors, and 10 failures, 10 purchases that weren't Yummies, 10 rock or paper throws, we can feel confident about using this approach. And it and the simulation approach will come together, and they will both say the same thing. Right? So that's it. How do you use the theory-based approach? You check that there's at least 10 successes and 10 failures. As soon as you do that, which is pretty common if you have a large enough sample size, you go, okay, I'm going to draw the picture. Once you've got your null hypothesis, you know the middle. Plug in your null hypothesis value and your sample size. That tells you your standard deviation, or standard error in this case. And then you have your picture. You can do your calculations of the p-value and z-score. You can give me a conclusion. So there's a little bit more in terms of steps that you have to take, I guess, because the computer was doing some of this stuff for you, but we don't actually need to simulate anymore. You can make the picture yourself. So there's some examples down below where we're going to go through together how to make this picture. So going to be lots of practice showing you how to make this picture. Right? It's not too bad. Once you get the hang of it, it's pretty quick. So what about the mean? What if our parameter is mu? Well, it's going to be very similar. We still have the predicting power that we have for a proportion that we talked about above. But in this case, there is a change. And so the change is, instead of using a normal distribution that we're trying to get to, we have to use something called the t-distribution. So they're very similar. They look very much the same. The only difference is the t-distribution has a little bit thicker tails, so that when you start to get into the extreme values on either side, the group of extreme values is a little bit thicker, and the middle is not quite as packed in as the normal distribution. Right? And so you could think of it as like it's a little bit more spread out. There's a little bit more spread. Not perfect, but that's kind of the idea you can think of. So where's the middle of this picture? Well, again, it's just mu. What did you tell me it was in your null hypothesis? Check. You give me the null, I tell you, boom, there's the middle of my picture. Okay, how spread out is it? How spread out is it? What's the standard error? Well, in general, and theoretically, the standard error would be sigma divided by the square root of n, where sigma, again, is the standard deviation of the whole population, and little n is your sample size. But we don't often know this value. This is a population parameter. It's a standard deviation, but that's still a population parameter. We don't know how to get this most of the time. So instead, we use little s over square root of n, where little s is our sample standard deviation. Right? Just because we almost never can know the true standard deviation of the population, so we've got to use just our sample. Right? So this again is another approximation to what it should be, but general works pretty well. So we can use this theory-based approach, and it'll be similar to our simulation-based approach, and the results will be similar as long as we have the conditions met. And what are the conditions for this? Well, we want our population to be roughly normally distributed. So that's the normal picture. We want to make sure that most people, or whatever we're looking at, are near the middle with some high, some low. Or if we get enough samples, if we get a big enough sample size, 20 plus for quantitative data, then we can feel pretty confident that this will work regardless of the shape of the original population distribution. All right, so here's a little summary of your validity conditions. Right? And we'll get into examples in the next video.